Now my next example is again on a manuscript, but it adds another dimension to the chemical maps, because when Stein from the University of Antwerp last visited us, he also brought his Alpha, the Bruker portable FTIR spectrometer, which he had mounted on a carriage to use it as a scanner. The great thing was that we could scan the same object and have both chemical element maps and functional group maps and combine those together, and that really helped specify the nature of some of the pigments that we were identifying. So we looked at this small fragment, which is about 17 by 17 centimeters. We got beautiful elemental maps, which really helped us understand the pigments and the painting techniques used. One of the things we looked at in particular was the gilding technique. And you can see in the gold map, you can clearly see the gold leaves, and you can also see the places where the two adjacent leaves overlap. Those are the brighter areas in the map. There's a double thickness of gold, and so you get a much stronger signal. You can actually measure the pieces of leaf, which can be interesting. And then we found there was calcium and there was iron in areas of gilding. So it's the kind of ground layer for gold that you expect. The iron is probably due to the presence of a red clay type material. And the calcium, when we get this far, the only thing we know is a calcium containing material. We can suppose it's gypsum, because that's what historically has been used. But we can't be absolutely sure. There's some little losses in the gilding, but they were too small for us to analyze by reflected spectroscopy, which would tell us if gypsum were present. They were just too small, we couldn't access them. So this is just a composite map. The blue areas, the bright blue areas, are the areas of loss. So the areas where there is no gold or not enough gold, and calcium really shines through. If you then do an FTIR scan and you map the sulfite stretching band, you can see that it maps to two leaves, which are pink. So again, that's the gypsum in the red lake, but also to lots of little dots, which match the areas of loss in the leaf. So that's the only place where the calcium signal is coming through, because we wouldn't be able to measure it through the gold leaf, obviously. But wherever there's a small loss or just a thin layer left remaining, we do see the sulfate stretch. So we can say it's calcium sulfate. I'm not going to say gypsum because we think it might not be gypsum, but it's definitely calcium sulfate. Something else that the combination with the FTIR mapping can help us do is distinguish between the different lead pigments, something that in the first example we hadn't been able to do, the red lead and lead white problem. So in this combination map, which is again tin and lead, the blue areas are tin alone, so that's the tin sulfite. The yellow areas are tin and lead, so that's a lead tin yellow. And then in red, you've got everything that's just lead, so those will be both lead white and red lead. And once you add the FTIR maps and you look at the lead oxide stretching and then the carbonate bending, and you map those, you can separate the red lead, the lead hydroxide, from the lead white, which is lead carbonate. And you can look for areas where both are present, which might be areas where red lead and lead white are mixed together, which we wouldn't be able, just based on color, we wouldn't be able to say.